Hello, I'm Ginger Pan, and again, you are welcome to find out my background by just plugging my name in Google, and you'll find all my background. And today, I'm going to talk about principal stresses. What are they? Why they are useful? Stress is, you think it's simple, but it's quite a strange thing. Let me explain why I think it's strange. Yeah? And let's think of the simplest possible case when we look at stress. So we just look at a piece of material like that, and you apply a force. Yeah? Apply a force. So that's what I'm trying to draw here. And you say, what's the stress? Everybody knows that. Stress is force divided by area. So it cannot be simpler than that. But if you think of this, say, force divided by area, which area? Well, I say, okay, of course I know which area. It's the cross-section area, yeah? Because this is a material, apply force, and this is a cross-sectional area we're talking about. Is a force divided by area gives me stress, yeah? Gives me stress. But why? Why it has to be this cross-section? Why it cannot be at an angle? It's easier to look here. So you're talking about this area. Like imagine that's an area, it's a third dimension. Why? Why can't I look at that cross-section? And you know that if you look at that cross-section, there will be stresses on that cross-section as well. So let's look at that. Now let's see what are we going to get. So let me review next part. So what I do is I sort of cut the material by half, so imaginary, so it's like a thought experiment. So I cut my material, throw it away, and then I consider this is a free body diagram, and I look at the forces. So I would have, this is the force you applied. What you can do is you can now decompose this force into a normal force, a normal component, and a tangential component. Yeah? I call it Fn and Ft with an angle alpha there. That alpha is arbitrary. It depends on which section you decide to look. It can be anything from sort of 0 all the way to 90 degrees. So your choice. So this is very simple. This is sort of balance of forces in physics. Yeah. So we can calculate tangential forces, normal force. So normal force will be F cos alpha, and corresponding to that normal force, there will be a normal stresses. Yeah. So that normal stress, yeah, is the normal force divided by the area. Now this area is different. We're not talking about that area anymore. We're talking about that area. Yeah. So that area. So this area, we're talking about these two different areas, and there is a simple relationship between them. So that area, this area is that area divided by cos alpha. This is all too simple. So then the normal stress is force, this force, divided by this area. So that gives me that, and I just do a little rearrangement. You end up with this rather simple equation. So that's what I'm saying. If I don't look at that cross-section area, I look at this area with the angle there, this angle is alpha, and you can calculate the stress using that equation. And you can do the same thing for the shear force. Yeah? Shear force, Ft is F sine alpha, and then do the same thing. You end up with another equation for your shear stresses. So in fact, even in this simple case, if I'm bloody-minded, I want to look at other angles, other directions, and you can always do this simple calculation, do them. Yeah, that's for curiosity, but why? Is it important? It's actually quite important. And let me explain why. When we do experiment and when we try to test material properties, we do simple tensile tests. Yeah, so we got a piece of steel, aluminum, whatever, and then we put them in this tensile test machine. We got a lot of that in our laboratory, so pull it apart, yeah, pull it apart. And when you do that, at some point, the material starts to yield. And in yielding, I've talked about yielding before. Yielding, what makes yield is permanent deformation, it's plastic deformation. And you get plastic deformation because you need to make those atoms to slide against each other. When they slide, you form this permanent deformation. So imagine this is my sample. I apply a tensile experiment, and you apply a force there and the yield. So, but you ask then, what's happening there? What is sliding against what? How, if you apply a force, the atoms, they just separate from each other a little bit. So what happened to sliding? Yeah, but we do know that the material yield, and that's that confusion because you're only thinking of stresses in that direction. What you need to do is to think this process. You realize that actually, if you look at a different angle, there are shear stresses, yeah, and those shear stresses make the material slide, yeah. So if you look at a different angle, so this guy is more important than this guy, yeah. So that's what you see when you do experiment. If you polish the surface and you apply force and then you reach the plastic deformation range, you see these slip bands forming, and you can actually observe them. The surface become rough, and then you see this slip band, and the slip bands form at 45 degrees because the shear stress, the maximum shear stress. If you look at that equation there, this lot, these two guys together become maximum. They are maximum when alpha is 45 degrees. So the shear stress, this shear stress, is maximum at 45 degrees. And that's why the sliding occurs at those 45 degrees. Yeah? So it's actually quite important, even in this really simple case, to look at stresses in other angles. Yeah? This is obvious, but that's, yeah, it's useful, but actually, you do need to look at other angles. So that's good, but then now let's come back to the principal stresses. So we are looking at, this is my representation of a sophisticated engineering structure with applied forces. And what you can do is you can focus on one point, yeah, so tiny point there. And then I draw a triangle around that point, but I'm blowing it up because if I draw a tiny small triangle, you can't see it. So I'm sort of enlarge that little triangle, make it large, but what I'm talking about is a point, around the point I draw a triangle there. So I'm doing an imaginary experiment, a thought experiment, like what I did here. Yeah? So I isolate that triangle out, and on that triangle you can appreciate, like what we did here, we expose different forces. Over here, you expose all the different forces, normal force, shear force, normal force, shear force, normal force, shear forces, yeah? And this is not even the most sophisticated because this is a plane stress situation. Some of you might know that. I mean, if you've been studying this. In three-dimensional, material are three-dimensional, and if you take a material out, you got this three-dimensional material, so you got stresses in all possible angles and directions, and that's even more complicated. But let's focus on this simple case. Even this case got too many forces. And then what you do is you follow the same process. Yeah, just do exactly what we did. Follow the same logic. You can find out this force here, call that Fn, and that Ft. Yeah, you can find out those two forces in terms of those forces, and therefore then you divide by an area, and it takes a long time, and then you find out these two stresses. So let me change it, use the black color. So here, let's say that's sigma n, this is tau n. You find out these two stresses. And then that is given by these two equations here. And the equations are not that complicated. You got these two equations here. Now, this C1 C2, I use a different symbol, so I'm correcting myself. So here, this C1, C2, and lambda, I don't want you to focus on them, but I know, and let me just show you what they are, and you can find them out from the books. I put the wrong name there, I call them A and B, now I'm correcting them, call them C1 and C2. So C1 is given by that expression there, and C2 is given by that expression there, and tiny lambda is given by that. And you notice that if you know the stresses, x and y, in the x and y direction, you know the shear stresses, and then you can calculate them. Yeah? They are messy equations, but anyway, they're just equations. Yeah? C1, C2, and lambda are given by that. But as I said, I don't want you to focus on them. So we know C1, so basically this C1, C2, and lambda, they play the same role as this sigma here. Yeah? That sigma here. So that sigma is stress in the direction you define. So they play the same role. Now, alpha can be anything. Yeah? Just like that alpha there. I look at any angle and I choose. So think of this. This log here, this log, sine something, the maximum value of sine something, or minimum value of something is either +1 or -1. So when this is either 1 or -1, this normal stress is either C1 plus C2 or C1 minus C2. So if I look at all the possible angles, possible directions here, look at all the possible angles, the maximum normal stress is either C1 plus C2 or C1 minus C2. So these are the principal stresses. Yeah, this guy, C1 plus C1, C1 plus C2, C1 minus C2 are called the principal stresses. They are the maximum or minimum direct stresses, yeah, in all when you of a particular point. And it's slightly more than that. We know that when sine something is either 1 or -1, the corresponding cos something is always 0. Yeah, that's mathematics. So when this guy is either maximum or minimum, this guy is 0. So when direct stress is either maximum or minimum, shear stress is 0. Yeah, probably 0. So now we come back to this idea of principal stress. So you do your stress analysis. So, and then you find out your stresses in the coordinate systems. You see, this is my y coordinate, this is my x coordinate, and you use your finite element analysis. You got the stresses of sigma x, sigma y, tau xy. You know them, yeah? You know them, yeah? And then you shoot those equations, you plug them in, you got your C1 and C2, tiny lambda. Lambda is not relevant here, unless you want to find out the directions of those principal directions. But let's focus on C1 and C2. So you know them. So then you can just calculate this maximum stress, yeah? C1 plus C2, C1 minus C2, and the shear stress is 0. And we know, I mean, there's slightly more than that. When this is minus plus 1, this thing is 0. So the two directions, +1, -1, they happen to be 90 degrees to each other. So what am I saying is this. This is an arbitrary direction you choose, you get a set of stresses. Now you can look at all the other possible angles. Yeah? You start from that, and then you sort of, the magnet is working, so you rotate, yeah, at a different angle. And when you reach, so you start from that angle, and you look, but you hit an angle there. And in that direction, the normal stresses are maximum or minimum. There is no shear stress. That direction is a principal direction, principal stress direction, and the stresses are the principal stresses. So these principal stresses are quite interesting, and they are principle because they don't depend on the coordinate you select. Whatever, you can do your stress analysis in any arbitrary coordinate you select, but then you can always follow this analysis. You find the angle, and in that angle, the direct stress are either maximum or minimum. Now, what is more important is this guy. You can look at the second equation here, and you know the maximum shear stress is simply C2, yeah, because when cos something is 1, that's C2. So tau maximum is C2. I'm holding that because that's important, is because for the same reason, the maximum shear stress is C2, and that guy is important. You want to calculate the maximum shear stress because it is the maximum shear stress that gives you plastic deformation. And this is von Mises. No, sorry, it's not von Mises. This is Tresca stress. This is exactly Tresca stress. It's a partial definition, but I can make it complete. But the basic idea of Tresca stress is just that. Okay, thank you very much.